Mr. Kyle,
Yeah?
pendulums are very peaceful, but I'm ready for something new.
Yeah, like what?
Let's blow stuff up.
That's a great idea!
Ha!
If there's anyone that likes a good explosion, it's us. But first we have to learn, number one, how to do it safely, and number two, why that's happening. So let's look at some chemical processes. I want to talk to you guys a little bit about chemical and physical changes. Those are two different kinds of changes. We know we get one or the other a few different ways. I'm going to take this towel, and if I scrunch it up, is it still a towel? It is, that's right. It's just in a different shape. This is a good representation of a physical change. It's still a towel, but it's just in a different shape. I can roll it up, still a towel, but a different shape. We can do the same thing with Play-Doh. I can make... This Play-Doh's kind of hard. I can make a little snaky out of Play-Doh. Get some eyes going. There he is. But is it still Play-Doh? It is. Even if I roll it up into a ball, we can get the Play-Doh ball back. This is just a physical change. We can do the same thing with a piece of paper. I can crumple it up, and it's still a physical change. But if I were to take this piece of paper, I'm just going to do it with a small part, and I were to do something like set it on fire, this would be a chemical change. Because once this paper burns up, it stops being a piece of paper. Don't do this at home. We're professionals. See, this is no longer paper, it's ash. I cannot unburn this paper. I can't get that paper back. That is a sign of a chemical change.
We have talked a lot about the teeniest, tiniest bits of everything. Do you remember what that's called? The tiniest building blocks of the air, your hair, your table, the food we eat, everything that has to do with you. Do you remember? That's right, it's atoms. Atoms make up everything in our world. And if we put these tiny atoms together that we cannot see at all, we make larger things called molecules. That's right. Now, we have talked before, if we could get out a super powerful microscope and see all the way down to the atomic level, atoms might look like Legos, where each type of Lego is a different kind of atom. So atoms are a lot like these Legos where we can make all sorts of different things out of them. We could make a house or a car or a little giraffe. We can take them apart and make new things. This is how atoms act. And scientists like to write down what they're putting together and taking apart using chemical formulas and equations. And today we're going to be making baking soda rockets, and this is the chemical equation for baking soda rockets. We start with the formula for baking soda. Its fancy name is sodium bicarbonate, and it has one sodium atom, one hydrogen atom, one carbon atom, and how many atoms of oxygen do you think it has? 3, yeah, that's what the little 3 means. If we add sodium bicarbonate to vinegar, which is really acetic acid, we've got 4 hydrogen, 2 carbon, and 2 oxygen. This little arrow means yields. So if we add baking soda to vinegar, it is going to yield carbon dioxide, which is CO2, and that is going to make bubbles. And there will be water, and there will be sodium and acetate left over. The really cool thing is that if you count up how many sodium are on this side of the arrow, you'll notice that it's the same as the number of sodium on this side of the equation. So if you count how many hydrogen, 1, 2, 3, 4, 5, it will be equal to the number on the other side of the equation. 1, 2, 3, 4, 5. Same thing with carbon. 3 carbon over here, 3 carbon over here, 5 oxygen on this side, and 5 oxygen on this side. So if we go back to our Legos, if we have them grouped as molecules on one side of the equation, we're just going to rearrange them, but it's the same number of atoms on the other side of the equation.
We're going to be doing our chemical reaction with some household products. This is vinegar. We find vinegar in some of our foods like ketchup and barbecue sauce. It's also in salad dressing. We may also clean some things with it. And then baking soda. We find baking soda in our toothpaste and some upset tummy medicines. We also use it a lot in cooking. It's the thing that forms all the little bubbles in our breads and our pancakes and our waffles and our muffins. I'm hungry now. Okay, we're gonna be doing one of these reactions and let's see which one we get. I'm gonna take, here's our jar, and I'm gonna use some vinegar I poured right in here. And then I'm going to take a big chunk of baking soda and drop it right in. And let's look for our reaction. What did we get? Color change? Heat exchange? That's right, we got bubbles. So we know we made a gas. Just like in our chemical formula, it says we made carbon dioxide.
So that chemical reaction that Mr. Kyle showed you with the vinegar and the baking soda is super fun to do in a film canister. If we fill the film canister about halfway full of vinegar, and we put a little bit of baking soda paste right in the dip of the lid where it can stick. Made a paste out of water and baking soda, so it's about the consistency of toothpaste. And then when we turn it over, it won't fall right into the vinegar. Make sure we're wearing our eye protection, then turn it over and step back. If there's a leak, it will sputter all over the table, and that's a fail. But science has a lot of mistakes. Let's try again. All right, take 2. Patience. Patience. This is when it'd be super tempting to go in and see if it's working, but it's not leaking, so something's happening inside the canister. So I know what you're thinking. If half a canister of vinegar and a little tiny blob of baking soda is good, wouldn't more vinegar and more baking soda make it better? Let's find out. You make a hypothesis. I'm going to add 3/4 of a canister of vinegar. And on the lid, I'm going to really gum it up, put a nice big blob on there. All right, we don't want it to fall off too early. Put our big blob on, snap it on, and stand back. That almost always fails. Why do you think it fails when it's only 3/4 of a canister full instead of half full? If you said there's not enough room for the air pressure to build up inside, you would be right. Because this is where physics takes over. The pressure inside of the canister has to be a lot greater than the pressure outside of the canister to overcome the resistance of the lid. Now the lid resists and resists and resists while the bubbles are building up. It goes, but eventually it can no longer contain the pressure. And when the pressure overcomes the resistance, kapow! You get the force of the rocket taking off. But you have to leave enough space for the pressure to build up. So we recommend either a third to a half full. Perfect rocket.
Those look like a lot of fun, Mrs. Reinfelder. I think I have some ideas of a prank we can pull later on.
Yeah.
There's lots of cool things going on with this canister. Number one is the energy conversion that's happening. In physics and in science, we say that you cannot create or lose energy. It can only change form from one to another. And what we're doing with this is changing the chemical energy held together in the bonds of these chemicals. We convert that into mechanical energy or motion energy, movement energy. Mrs. Reinfelder, that was so cool. Let's go make some more baking soda rockets.
Bye guys,
Bye.
go make some of your own. You can just get the canisters online. They're called film canisters and they're super cheap. And you probably have baking soda and vinegar around your house. Don't forget your eye protection and stand back. It's probably best to have an adult supervise.
Yeah, I
but
have
it's
Mrs.
a ton of
Reinfelder.
a fan.
Bye.
Bye.